And we finished with this stuff on Tuesday. We did have these reactions that were listed out there. You do have a Socrative app question that you were to have answered when you come in here today, just to see how you were doing on your electrolytes. And if we check this here real quickly, we should see that the calcium bromide was in fact a strong electrolyte. And how could we look at this and know that it was a strong electrolyte? It's an ionic compound. And what does this mean? Dissolved in water. So if you have an ionic compound dissolved in water, this is going to be one that is a strong electrolyte. Okay, so remember, a strong electrolyte. Well, an electrolyte to begin with is a substance that conducts electricity when dissolved in water. In order to conduct electricity, we have to have ions in solution. So this here is an ionic compound. We have it dissolved in water. This is going to be a strong electrolyte. Now, we come back and look at then these that we looked at the end of the hour. Our topic here for chapter 14 is acids and bases. We said that there was a number of these here that we are going to need to memorize, and that list of ones to memorize is right here. Now, of course, memorize at this stage might mean to put it on your note card. I did have some people ask at the end of the hour, what can we put on the note card? Basically, you can put down anything you wish on there. If you're worried about forgetting your polyatomic ions, write your polyatomic ions on there. If you wish to have a worked out problem on there, put a worked out problem on there. Whatever it is you want to put on that card, you may put on that card. So, as you look at these are the ones that you ought to be memorizing. And specifically, if you're going to memorize anything, these are the two columns you should memorize. You should memorize the strong acids and the strong bases. And the reason why you should learn these is because if you learn the strong acids and learn the strong bases, any other acid you encounter is going to be a weak acid. So this here is a complete list of strong acids. And this here is a complete list of strong bases. So again, any other acid you encounter, if you don't see it anywhere on either of these lists, it's going to be a weak acid. And then likewise, if you don't see anything on the list here, it's going to be a weak base. Now we talk about the group 1A and group 2A hydroxides. What do we mean by group 1A and group 2A? What do these mean? On the periodic table, right. So we come back here, here's your group 1A and your group 2A. And so if we have these as hydroxides, these are going to be your strong bases. So lithium hydroxide, sodium hydroxide, potassium hydroxide, rubidium hydroxide, calcium hydroxide. So all of the hydroxides from groups 1A and 2A, with the exception of beryllium and magnesium hydroxide. And the beryllium and magnesium hydroxide would be the ones that would be over here as part of the all other hydroxides. So again, these are ones you should know. So let's just check your understanding here real quickly on these. I do have a Socrative app question to see how well we do with it. We have H2CO3. H2CO3. How would we classify H2CO3? Would it be a strong acid, a weak acid, strong base, or a weak base? Okay, let's get your answers locked in here. Give you about 5 seconds. We'll count down. 5, 4, 3, 2, 1. Whoa. And how about this? There we go. This would be a weak acid. First of all, what's our clue that this is an acid?
H2.
All right, we have the hydrogen written where? In front of the formula. And so then this is going to be a weak acid because it is not in our list of strong acids. Remember that this is a complete list of strong acids. Any other acid that isn't on this list would be classified as a weak acid. So any questions on this one here? All right, we're going to finish the course by looking at pHs. And pHs happens to be one of those things. For some of you it's going to be really, really easy. For some of you it's going to probably be fairly difficult. And before we begin these, what I'd like for you to do here is to see what you already know. Talk with a neighbor here. Talk with a neighbor. And ask yourself, which of the following pHs is or are neutral? Once you think you have your answer or answers, pop them in.
Sorry.
Okay, let's take about 10 seconds to get your answers locked in. And we'll count down. 5, 4, 3, 2, 1. We're not going to reveal yet because your next one is to determine which of these is acidic. And that's is or are. There could be more than one answer. So select all that apply. And the next question coming up after this is which pH values are basic. So we'll count down here. 5, 4, 3, 2, 1. And then answer this one here. Which of the following pH values is or are basic? Select all of them that apply. So I'll give you a chance to lock in your answers here. And now we're going to go back and check out how we answered. And start with this one. Which one is neutral? 7. Very good. pH of 7 is a neutral pH. It is the only one in all of them that is neutral. Next up, which of these is acidic?
A and B.
1 and 4. How about that? 1 and 4. The pH is less than 7. We say that the solution is acidic, which of course means
10 and 13 are basic.
10 and 13 here are basic. So these are facts we need to know about the pH scale. If you write down these pHs, once again, on the pH scale, sitting here in the middle is going to be a neutral pH. Out here we will say that these represent a base. Out here we will say these represent an acid. So a neutral pH again is 7. pH values can go down to 0, and anything in this range is going to be an acid. And then pHs can go up to 14. Anything in this range here would be a base. So again, this here is your range of pHs. And actually, it is possible to have pH values that are negative, though they're not common. We can also have pHs that are greater than 14, though they aren't common. Yes, Grant.
So it doesn't say so in the book, at least unless I didn't see it. But what does pH stand for?
pH. Glad you asked. pH stands for the power of hydrogen. Power of hydrogen. Stands for the power of hydrogen. And that's because, boy, I just set you up on this one perfectly. Because the way that we're going to calculate this one is we said that pH is equal to the negative logarithm of H plus. Oh my gosh, this is really the last day? You're going to throw that kind of crap at us? How many know logs? Okay. How many have maybe never, and that's okay if you admit it, how many maybe never seen it before? Logs. Okay? And maybe it's been a while. Okay? Now logarithms, and this is where the term power of hydrogen comes from. Logarithms is a value that if we were to look at something like this, if we want to know what the logarithm is of 10 to the negative 8th, the logarithm of 10 to the negative 8 is, help me out, negative 8. The logarithm of 10 to the 4th is equal to 4. So that means the logarithm of 10 to the x is equal to x. Okay, so these are some very simple values of logs. And this is, now logarithms come in different flavors. This is what we call a base 10 logarithm. We have all sorts of bases. If we had a base 2 logarithm, we'd say that a base 2 logarithm of 2 to the 8th would be equal to 8. Now, you maybe haven't gotten to other bases. I don't remember when you do that. Is that that's not an intro algebra topic. It can't be, is it? So, anyhow, the ones that we are going to work with in here are base 10 logarithms. And so, again, this is going to go back to why it's called the power of hydrogen. So now, a couple other things that we should look at here. Another one is what these square brackets stand for. These square brackets stand for molarity. So when you see the square brackets around a quantity, that means we want to take the molar concentration of those values. And so, while this here happens to be what we say the old definition of pH, the new definition of pH looks like this. We define as being the negative logarithm of the hydronium ion concentration. And so this is a newer, a more modern definition. Now the reason why we have a more newer or modern definition is back in the days when pH was defined, we didn't really know that there was such a thing as a hydronium ion. Because we looked at something like an acid, like HCl or HBr, and we see that all of these here contain the element hydrogen. Okay? And so there must have been something that was involved with the power of hydrogen. But it turns out that they had been looking at things wrong all along. And if we went and looked at what a hydrogen ion really is, we have to first start by looking at what a hydrogen atom is. And if we look at what a hydrogen atom is, let's go back to the most basic of construction of a hydrogen atom. What are we going to find in the nucleus of a hydrogen atom? What's going to be in the middle? Protons, right? And how many protons? Just one. And where do we get the one from?
The atomic number.
Atomic number. Right. We look here at hydrogen and we see its atomic number is 1. So a hydrogen atom is going to have 1 proton, and sitting out here in the electron cloud we're going to have 1 electron. So it's 1 proton and 1 electron. Well, now if we change this from a hydrogen atom to a hydrogen ion, and ask yourself, well, what the heck is a hydrogen ion? What does a plus charge mean has happened?
Gain its or proton.
Oh, I hear all sorts of answers. I hear gaining protons, I hear losing protons, I hear gaining electrons, losing electrons. What does this mean? Loses electrons, right. Remember that the only thing that can be gained or lost is electrons. That's because they're here on the outside. So this is going to lose an electron. If we lose an electron, what are we left with? A proton, exactly. So a hydrogen ion is really the same thing as a proton. Hydrogen ion and a proton are the same thing. Now it turns out, remember when we talked about the size of the nucleus compared to the size of an atom, I think we made the analogy in here. It was like comparing a housefly to the size of a stadium, like Target Field or the Metrodome. So that would be, again, just like comparing a fly to the size of the Metrodome as comparing the nucleus to the size of an atom. So what this means is that this proton is really, really tiny, but it has a full positive charge. And because it's really, really tiny and has a full positive charge, that means that that charge is super, super, super concentrated. And if the charge is super, super concentrated and it's positive, that means that something that's positive charge and super concentrated positive charge is going to seek out something that has a negative charge. Well, it turns out that if it's in water, what it does is it seeks out molecules of water, and we basically look at a water molecule like this, and a water molecule has these lone pairs on it. And so it turns out that these hydrogen ions are very much attracted to those lone pairs. So when they are attracted to those lone pairs, what happens is that that hydrogen basically attaches onto that water molecule. So your water molecule is looking like this. It has an attraction for this pair of electrons and basically winds up latching onto it. And once it latches onto it, we wind up forming another bond here, and we form this ion, which of course we now know what this ion is. This is called a hydronium ion. So really what happens today, and what we know that happens, is that hydrogen ions, while they might form, they don't stay there by themselves. If they do form, because their charge is so positively concentrated, it seeks out a lone pair on these water molecules and winds up forming a hydronium ion. So that's why we often wind up using these two definitions interchangeably. In fact, your author still is showing this. I mean, we do this for intro students, but if you go beyond this class, and I believe he does show this right there, but if you go beyond this class, we rarely look at this formula. We look at this one here as being the way we define it. But we still refer to it as being the power of hydrogen. So, see, you didn't know you were asking such a great question. Okay? So, any other questions on this? All right, so now, with this, one of the things we can look at is what's called the self-ionization of water. The self-ionization of water. And what this means is that molecules of water can ionize all by itself. And what happens is that two molecules of water will react with each other. When they react with each other, they are going to yield hydronium ions and hydroxide ions. Now again, that would be just like me taking water out of here. This is pure water. If I open this up here and put some water in here, it means it's going to contain some ions. Now we did this the other day, and we tested it to see whether or not it conducts electricity. And what did we find out when we took pure water? It didn't conduct, right? So if it didn't conduct, what is that telling us about the amount of ions that's in there? A whole bunch or very little? Very little, right? Because if it's going to conduct electricity, that means it has to contain ions. It has to have a whole bunch of ions in there. So the amount that's in there must be really, really small. And it turns out that we have measured this amount, and the amount that's in there is actually 10 to the negative 7th molar at a temperature of 25 degrees Celsius. And 10 to the negative 7th molar would be like 1/10,000,000th of a mole contained in the solution. And again, this is at 25 degrees Celsius. So now, if we know that information, what we can do is we can calculate the pH. Let's calculate the pH of pure water. At 25 degrees Celsius. So if we want to calculate this now, our formula says that the pH is equal to the negative logarithm of the hydronium ion concentration. And remember now, the concentration is what these square brackets stand for, the concentration in units of molarity. And what is the concentration of hydronium ions in pure water? All right, here it is 10 to the negative 7th. So we substitute that in. We want to take the negative logarithm of 10 to the negative 7. But now, we just did like about a week worth of algebra. Remember now that the logarithm of 10 to the negative 7 is? Negative 7. So the logarithm of 10 to the negative 7 is negative 7, but we have the negative sign out in front, which means we are going to change the sign. So we're going to say it's going to be the opposite of negative 7, which is going to give us a value of 7. And so what is a neutral pH? 7. And that's where that number comes from. So when you've heard or learned of this number of a pH of 7 being neutral for all these years, the reason why it's a neutral pH is because the hydronium ion concentration in pure water at 25 degrees Celsius is 10 to the negative 7th molar. Now there's another value that we look at here, and it's what's called the pOH. And so we are going to calculate the pOH of pure water at 25 degrees Celsius. Now it turns out that this P stands for the power of. But now in this case it's going to be the power of hydroxide. Which means we're going to calculate it by taking the negative logarithm of the hydroxide ion concentration. So now if you're writing down important formulas to memorize or to put on your card, these are going to be two important equations to put down. You, of course, have heard about pH before. Many of you have not had chemistry before. I've probably never heard of pOH before. But it is a real thing. But now we also know what the hydroxide ion concentration is of pure water. The hydroxide ion concentration of pure water is 10 to the negative 7th molar. So we can then substitute that in. Put in 10 to the negative 7. If we then take the logarithm of 10 to the negative 7, the logarithm of 10 to the negative 7 is negative 7. And the opposite of negative 7 is going to be positive 7. And so we say that the pOH of pure water is also equal to 7. And this leads to a relationship. Now we would, in a more advanced chemistry class, prove this a little bit further, but it leads to a third relationship or equation you need to know for this chapter, and that is that the sum of the pH and pOH is always going to sum to be 14. We actually read it as 14.00, because if we start getting to significant figures, we would see actually that I lied to you a little bit about these concentrations. These are actually 1.0 times 10 to the negative 7th. So 1.0 times 10 to the negative 7. And one of the reasons why we use a temperature of 25 degrees Celsius is because at 25 degrees Celsius it turns out that the concentration is exactly 1 times 10 to the negative 7th molar. It's a little bit warmer than room temperature. Like right now in here it's probably about 22, maybe 23 degrees Celsius. So 25 degrees Celsius is just a little bit warmer. So let's see what we now know. Let's say we have this example. We'd like to know if the hydronium ion concentration is equal to 10 to the negative 4th molar. And don't shout out the answer here, because these are the next two Socrative app questions. We'd like to know what is the pH and the pOH. What is the pH and the pOH? So we'll go ahead and put these up here. There we go. We'd like to know what is the pH and the pOH. The next question is going to be to give the pOH. So this first one, it looks like we're just answering the pH. Now if anybody needs calculators, we are going to need calculators here in just a bit for more involved calculations. Anybody need a calculator today? Alright, I need some collateral. I know you have fancy keys. More, right? Anybody else need a calculator? Thank you. Full of gas, I hope. Anybody else need one? It's okay, you can help each other out. The next question is going to be, what is the POH? So be prepared to answer the next one. What is the POH? So I'll give you about 15 more seconds on this one. And I'll flip over to the next one. What do you answer the POH? And here comes the next one. There we go. What is the POH? All right, let's get your answers locked in, please. So we'll check these out, see how we did. Maybe today ain't so darn bad after all. So we'll show the answers here. The correct answer is a pH of 4. Wonderful. pH of 4. Great. Is that perfect? Gosh, I think that might be the first time all semester. You guys are giving me chills. Okay, then the POH isn't going to be 0. It's not going to be 4. It's not going to be 6. The POH is going to be 10. And that one, remember that the sum of the pH and the POH must sum to be
14.
14. So if the pH is 4, how do you get the POH?
14 minus 4.
14 minus 4, exactly. We take 14 minus 4, which is going to give us an answer of 10. So showing your work real quickly here, we show it's a negative logarithm of 10 to the negative 4, which is going to be the opposite of negative 4 or 4. We then know that the sum of the pH and the POH sums to be 14.00. Since the pH is equal to 4, that must mean that the POH must be 10, because again, these two here must sum to be 14. Any questions on these? Yes, sir.
According to sig-fig rules, should we also put pH as 4.00 and POH as 10.00?
We haven't looked at any sig-fig rules yet. That's what we're going to do next. See, you must have known what we were going to do next. So significant figures when it comes to pHs are a little bit more, well, not next. It's the next thing after what's next. So just a real quick thing on the pH, and we are going to answer that one here. Let's say that we were to talk about some acid rain as an example. Here we go. And now we want to compare pHs. And let's say that we talk about some rain. You can answer this one now if you want, or you can wait here just a bit. The question here is, how acidic is a solution that has a pH of 3 compared to a solution that has a pH of 6? So now, one of the things you can do with this is you can make a table. And if you make a table, and we look at the pH on one side, what the heck is happening here? I don't know why it went down there. pH on one side, and the hydronium ion concentration on the other side. Let's say that we want to look at pHs of 7, 6, 5, 4, and 3. So if we want to look at a hydronium ion concentration at a pH of 7, remember at a pH of 7, this here would be equal to 10 to the negative 7 molar. And at a pH of 6, it would be 10 to the negative 6 molar. At a pH of 5, this would be 10 to the negative 5. pH of 4 would be 10 to the negative 4th. pH of 3 would be 10 to the negative 3rd molar. So now, if you go back to your question, the question was, how acidic is a solution that has a pH of 3 compared to a pH of 6? And let's get answers locked in here, please. So half as acidic, twice as acidic, 30 times more acidic, or 1,000 times more acidic. And we'll count down here. 5, 4, 3, 2, 1. Correct answer is 1,000 times as acidic. Now, how do we get that? Remember, at a pH of 6, the hydronium ion concentration is 10 to the negative 6 molar. At a pH of 3, it is 10 to the negative 3rd molar. These two differ from each other by a factor of 10 to the 3rd, which is 1,000. So what this brings up is that each jump in pH unit is equal to a factor of 10. And what that means is that the difference between these is a factor of 10. The difference between these is a factor of 10. The difference between these is a factor of 10. So we don't take 10 plus 10 plus 10. We take 10 times 10 times 10, which is going to give us a factor of 1,000. Okay, and this is what's astonishing to a lot of people, because you go and listen in the news, and this is what goes back to the power of hydrogen that we first talked about here today. The general public does not understand logarithms and things based on logarithmic scales. If you look at a pH of 3 and a pH of 6, to the general public, that looks like a factor of 2. Okay? But what we need to realize is that pH is based on the logarithmic system. There's other things that are out there that are based on the log system that people don't understand. And another one of those is the Richter scale. And what does the Richter scale measure? Earthquakes. Okay, and it talks about the magnitude of the earthquakes. And so if you had an earthquake of a magnitude 6 versus a magnitude 7, which one is a stronger earthquake?
Magnitude 7.
Magnitude 7. You know how many times more intense a magnitude 7 is than a magnitude 6? 10 times. Okay, it's actually 10 times. And if you have a magnitude 6 versus a magnitude 8, that is a factor of 100 times. Okay, so that's why when things are in the news about earthquakes, you're actually going to hear debates. Is this a 6.1 or is this a 6.2? Is it a 6.5 or is it a 6.7? Because even if we're talking about 2 decimal places indicates a very huge difference in terms of the impact or strength of those earthquakes. So when we talk about an earthquake, like the one that caused the tsunami near Japan, I guess it's now about 5 or 6 years ago, that was a magnitude 9.2 earthquake. Okay, that was a very, very super intense earthquake that generated that tsunami. If you look at the one that occurred in Haiti now, and that's probably been about 7 or 8 years ago, that was about a magnitude 7. But it turns out that the difference between Haiti and Japan is, Japan, even though that earthquake was 100 times more intense, their infrastructure was a whole lot stronger than in Haiti, which is a much poorer country. And being much poorer, they did not have the infrastructure in place. And so magnitude 7, even though it was 100 times or 1/100th the strength, they saw a lot more damage because their buildings and stuff were not reinforced the same way. Now the Japanese saw a lot of damage simply because it was 100 times more intense. But again, their infrastructure was in place. So inland, outside away from the tsunami, they did not suffer near the impact that Haiti did because of the difference in infrastructure. So when we talk about acids and bases, we see kind of the same thing. The general public doesn't understand these types of things. So one of the things we could talk about is acid rain. And we could talk about normal unpolluted rain. Normal unpolluted rain, turns out most people think that normal unpolluted rain has a pH equal to 7. It doesn't. Actually, normal unpolluted rain has a pH of approximately 6. And the reason why it has a pH of approximately 6 is because it turns out that you and I are all exhaling something that makes water acidic. In fact, I know at least a couple of you did the cabbage juice lab in here. But if you exhale carbon dioxide, it turns out that when you exhale carbon dioxide will react with water to yield this stuff right here. And of course, this was our second Socratic math question today. Remember, we classify H2CO3 as a weak acid. It's a weak acid. This is carbonic acid. And when we burn stuff, organic material, it also gives off carbon dioxide. Volcanoes put out carbon dioxide. There's always some carbon dioxide that's in the air that's going to give us a slightly acidic pH. But nature's able to handle that. Turns out then that when we polluted rain may sometimes have a pH as low as 6 or as low as 3. And where this comes from is a couple of different things. First of all, we might burn some coal that contains sulfur. And if we burn coal that contains sulfur, it turns out sulfur can react with oxygen to produce sulfur dioxide. And the sulfur dioxide goes up into the atmosphere and reacts in the higher reaches of the atmosphere to produce sulfur trioxide. And so you get something that looks like this. Well, then this reacts even further. Turns out that the H2O, which comes from water droplets and the evaporation of water, will react with the sulfur trioxide to yield H2SO4. Well, now, if you had to classify H2SO4, we go back to where we started today. H2SO4 is classified as a
strong acid.
Strong acid, right here. And it turns out, so the sulfur, this comes from burning coal that contains sulfur. And we're never going to avoid sulfur in our coal, simply because coal comes from millions of years of compression of decayed matter. And you and I, we eat stuff that contains proteins, and proteins contain sulfur. So there's going to be sulfur always in coal. The other main source of pollution for acid rain comes from simply internal combustion engines. Anybody know what an internal combustion engine is? And what is it?
Your car.
It's what you have in your car. That's what got pretty much everyone here today, is your car. And so, of course, what happens in your car is your car takes in air which contains nitrogen and oxygen. And when it comes into your car, that comes in at a very high temperature and a very high pressure. So when you pressurize air at a very high temperature and pressure, even while you're burning gasoline, it turns out that you also burn some of the nitrogen in the air, and this nitrogen turns into what we call nitrogen oxides. And I'm putting a subscript of X and Y in there for the simple reason that there's all sorts of nitrogen oxides that form. We can have NO2, N2O, NO, N2O4. There's all sorts of nitrogen oxides that form. But ultimately what happens then is that these nitrogen oxides will react with water and yield HNO3, which is classified as nitric acid, which is a strong acid. So what happens then when we make acid rain is that the acid rain comes from the fact that when we're doing things that aren't exactly natural, like pressurizing air at high temperatures or burning coal, that's when we start putting these more acidic components into the air, and that's what drops the pH so low. And so again, when we're talking about acid rain having a pH as low as 3, that's not like it's twice as acidic or anything like that. Again, it's significant because it can be 1,000 times as acidic. So you wonder why scientists get worked up, environmentalists get worked up about this stuff. It's because the general public, again, does not understand how things like pH work or are represented. So that's kind of off my soapbox a little bit. We're going to wrap up, though, by asking or answering your question about significant figures. Any questions on acid rain here first? All right. Then, on your calculator, here's what we need to find. You need to find these buttons. You need to find a log button. You need to find a sign changing button. And you need to find a scientific notation button. So you need to find these 3 buttons, and this might be like a times 10 raised to the y power. So everybody find these. You need to find the log. You need to find your sign changing button. Sign changing button might also look like this. And then you need to find your scientific notation button. So here's what we're going to do. We are going to calculate some pHs now, which are a little bit more involved. And we're going to start by calculating the pH of a solution where the hydronium ion concentration is equal to 5.6 times 10 to the negative 5th molar. So to do this one, we start off with our formula, which says the pH is equal to the negative logarithm of 5.6 times 10 to the negative 5th. Now here's how you enter it into your calculator. If you have a TI graphing calculator, here's the convention for a TI graphing calculator. First thing you're going to put in is you're going to put in the negative sign first. You're going to put in the sign changer. Then you're going to put in the log button. And then it should pop up some parentheses. In the parentheses, you're going to put 5.6. You'll put in EE and then negative 5. And then you're going to close the parentheses and then you're going to hit enter. So here's your convention for entering it into the TI graphing calculator. Now the conventions on other calculators may vary. If you have an older like Casio or Sharp calculator, maybe only a single line display, your convention looks something like this. It might be 5.6. You're going to hit the EXP button or your EE button. Then you're going to hit your sign changing button. And then you're going to hit the log button. And then you're going to hit your plus/minus key again. So again, this is your older calculators. This would be your newer graphing type calculators. And if you do all of this and have done it correctly, you should wind up with an answer of 4.25. So now, if you cannot get that answer, 4.25, we'll talk about sig figs in just a minute. Run it through your calculator. If you can't get it on your calculator, raise your hand here so we can make sure you get that number on your calculator. Everybody need it. On yours. Yours times 2. Yeah. Okay. Anybody else? Let's see. Yours is probably going to be, let's see, 4.6. Negative 5. And then I can do it as a log. There you go. Plus/minus. Anybody else? Okay. So now, once you do that, we'll talk about how we round and why we round in a minute. We're still getting to that question. Let's say we change this a little bit now. Let's say that we're going to change the hydronium ion concentration. Let's see, before we did 5.6, we are now going to say that this here is the uncertain digit, which it is. This measurement here now has how many significant figures? It has 2 significant figures. So the uncertain digit is the 6. So we're going to change that uncertain digit to a 7. So we're going to say now we have 5.7 times 10 to the negative 5th molar. So now if we have 5.7 times 10 to the negative 5th molar, let's go ahead and calculate the pH using this. And the whole point of this is to learn our sig figs. So we'll take the negative logarithm of there we go. Negative log of 5.6 e negative 5. And if you do this, well, it's 5.7, sorry, we wind up with an answer of 4.24. So 4.24 is what we get this time. Now notice when we did this, what changed was this digit right here. This is what's changed. And the reason for that is because if we look at this number right here, this number, this exponent, is actually what determines the number that goes in front of the decimal. So this number here is what determines what goes in front of the decimal. And it's these values here that determine what goes after the decimal. Okay, now where that's significant is this. That means that if your concentration has 2 significant figures, that means your pH should have 2 decimal places. Okay? So again, because this pH has, or this concentration has 2 significant figures, that means your pH here should have 2 decimal places. Now if you're not sure of this, let's say that we change this just a little bit. Let's keep the numbers the same now. Let's change the exponent. Let's change the exponent, in this case, to 5.7 times 10 to the negative 4th molar. Let's say we calculate the pH for this one. So go ahead and try it. See what you wind up with. See, I don't even need to look this one up because now the number is going to change to 3.24. So notice all the digits after the decimal stay the same. So by changing the exponent here, the exponent changes the number in front of the decimal. So the numbers after the decimal are determined by this value. The numbers in front of the decimal are determined by the exponent, which again goes back to the power of hydrogen in here. So try this one, and this is your next one on the Socrative app. We have the hydronium ion concentration of 5.7 times 10 to the negative 6th molar. What is the pH? Oh, get it up on the Socrative app. If the hydronium ion concentration is 5.6 times 10, 5.7 times 10 to the negative 6th molar, what is the pH? You have the answer with the correct number of decimal places. Okay, let's check the answers out here. And we'll count down 5, 4, 3, 2, 1. And good. 5.24. 5.24 is what we come up with. Great. Which means you're all set then for this last piece. So now we've looked at hydronium ion, we've looked at hydroxide ion. Now let's talk about actual acids and bases. You are only going to be responsible for calculating the pHs of strong acids and strong bases. The pHs of weak acids and weak bases, the mathematics require pretty much an entire chapter of additional knowledge. And that's something we do in our more advanced classes. But if we want to calculate these, what we say is that in a strong acid, the hydronium ion concentration is equal to the concentration of the acid itself. And in a strong base, what we say is that the concentration of hydroxide ions is equal to the concentration of the base times the number of hydroxide ions in the formula. So again, in a strong acid, the hydronium ion concentration is equal to that concentration of acid. The pH of a strong base, the hydroxide ion concentration is equal to the base times the number of hydroxide ions in the formula. So then, if we want to calculate the pH of something like this, we'd like to know what is the pH of 0.10 molar HCl. What is the pH of 0.10 molar HCl? So before you answer this, you ask yourself, how do we classify HCl? Is this a strong acid, weak acid, strong base, weak base? What is it? When we come back here, we see it is a strong acid. If it's a strong acid, what that means is that this concentration is equal to the concentration of hydronium ions. So in this case here, the concentration of hydronium ions is equal to 0.10 molar. And again, this comes from the fact that this here is a strong acid. So because it's a strong acid, we then can go ahead and calculate the pH by saying we're going to take the negative logarithm of 0.10. If we go to our calculators and punch that in, we are then going to take negative, and try this out because we've done mostly ones with scientific notation. We'll take the negative log of 0.10. Once we do that, we see that we wind up with an answer of 1. We end up with an answer of 1. Now, how many significant figures should this have? Or how many decimal places? Should have 2. And that's because this value here has 2 significant figures. Because it has 2 significant figures, that must mean that our pH has 2 decimal places. And the answer here would be 1.00. We go back to our pH scale. We ask that this makes sense. pH is way back here. Where do we have that scale? Somewhere here. Here we go. Definitely is going to be an acid. Sits down here on the far end by 0. Answer that makes sense. So we do the next one. We want to know what is the pH of 0.10 molar sodium hydroxide. Well, if we want to know the pH of 0.10 molar sodium hydroxide, we need to first be able to classify sodium hydroxide. Sodium hydroxide would be classified as a strong base. So now, because it's a strong base, what this tells us is that the concentration of hydroxide ions is going to be equal to the concentration of the base, which is 0.10, and we're going to multiply it by the number of hydroxide ions in the formula, which is 1. So the concentration of hydroxide ions in this case is going to be equal to 0.10 molar times 1, which is going to give us an answer of 0.10 molar. Now, of course, in this case, we can't calculate the pH directly because we don't have the hydronium ion concentration. What we do have in this case is the hydroxide ion concentration, which means we should first be able to find the pOH. So we find the pOH in this case by taking the negative logarithm of the hydroxide ion concentration, which means we are going to take the negative logarithm of 0.10. Now, we already calculated what the negative logarithm of 0.10 is up above. The answer to that is
1.00.
1.00. But remember now that this here is the pOH. If we want to find the pH, remember that the pH and the pOH sum to be 14.00. Which means if we want to find the pH, we're going to have to subtract the
1.0.
pOH from each side. So this disappears. We take 14.00 minus 1.00. We wind up with an answer of 13.00. We come back then to our table of pHs and say, does this make sense? It does, because the pH here should be really, really high. Which takes us down to the very last problem. And the very last problem is going to be this. And try this out. See if you understand it now. We want to find out what is the pH of 0.0023 molar barium hydroxide. What is the pH of 0.0023 molar barium hydroxide? Of course, now when you look at this one has how many hydroxide ions? 2, which means you're going to take the concentration and multiply it by 2. And this is your last shot on the Socrative app for the semester. What the heck, let's just show your answers on this one and see if your answer falls in line with your peers. Compare your answers before you commit yourself. I'm seeing 3 different answers up here, 4 different answers. The correct answer is already shown up here though. So it is one of these numbers that is up here. And it is the number that is showing up most frequently. Alright, so if you don't have that answer, find someone that does have that answer so they can explain it to you. It is 11.66. that's all I have for you here today. But you do need to come up with 11.66. I do want to say that it's been my pleasure having you as students this semester. I do appreciate your participation. Thank you. But check it out here. I'll come around and help you.